Okay, we've got problem, I forget what the number is now. Let this be a sphere viewed, say, along the x-axis or along any axis through the origin. Where Z is here. Then a line Z equals square root of x squared plus y squared here will be an angle phi equals pi over 4 relative to the z-axis. Since this is just in cross-section, this is a line where the rise equals the run. Then, of course, we have the other side. Where again we have pi over 4, because this, of course, this line rotates around the z-axis, giving us a cone in a section then out of the sphere. No, just do what you do. Let's pull the door. Okay. You're good. Excuse the interruption. Washing the floor, buffing the floor outside. It's going to be a little background noise, but I pulled the door. I don't think it'll distract much. Okay, sorry. Okay, so we have this, and then we have I think it's given in the book as 2z equals the square root of x squared plus y squared. We write that as z is the square root of x squared plus y squared. Slope 1/2. Here and here. And I'll indicate the angle here. And that's phi equals the arctangent of 1/2. So this also cuts a conic section out of the sphere, not a conic section, section out of the sphere, which is a cone with apex at the origin. Anyhow, so when these two lines rotated, of course, about the z-axis, we're going to cut out a sort of a wedge-shaped cone type chunk out of the sphere. And what we want to do is we find its volume, we find its moment of inertia, we can find just about anything. Okay? So if we're trying to do moment of inertia, there's a convenience to using cylindrical coordinates, because for any point in this region, r is the distance from the origin. So our cylindrical coordinate r would be natural. On the other hand, this thing's bounded by shapes that are natural to describe in spherical coordinates. So it's probably worthwhile looking at how you set up this integral in spherical coordinates. So let's just say we've got a point here, and the point is a sample point within some region. It's rho star theta star phi star, and it's within region dimensions. It's approximately a rectangular region, but its dimensions are d rho rho d phi and rho sine phi d theta. Okay, the distance from the z-axis is rho sine phi. And this all should be obvious. I'm not going to draw it all out. Because really what we're doing is we're looking at the correspondence, and presumably we understand all of this. Okay, so that the contribution to the moment of inertia is density times volume, and the volume of the region. I think we're assuming constant density. Okay, assuming constant density, so it's I'm writing this down in the order I don't want to, but I'll do it. It's density times d rho. Well, let's multiply these out. Let's write it out as the standard product of these things. Rho squared d rho d phi. That's rho squared sine phi. There's a sine phi up there, right? So the rho squared sine phi d rho d theta d phi times rho sine phi squared, which is then going to be density times rho cubed sine cubed phi d rho d theta d phi. And if we're talking about sample point rho star, d rho star cubed and sine phi star, theta is going to go from 0 to 2 pi, so I'm just going to get a 2 pi out of it. Okay, and from this we find that I is going to be the integral then we'll just integrate in this order. Rho goes from 0 to a, radius of the sphere is a. Theta goes from 0 to 2 pi, and phi goes from 0 to pi. Delta comes out in front. We've got rho cubed sine cubed phi d rho d theta d phi. And that's a pretty easy integral. Okay, rho integrate, you're going to have an 8 to the 4th over 4 doing the rho integral. You have sine cubed theta, so you're going to let u equal sine theta, and sine phi. You're going to let u equal sine phi, so du equals cosine phi, d phi. And you're going to have like a 1 minus sine squared times a sine and all that stuff. So that it's easy to integrate an odd power of the sine. And then your d theta, and I don't know why I keep writing theta instead of phi. But your phi integral going to go, or your theta integral is going to go from 0 to 2 pi. It's just going to give you 2 pi. So by the time you get to the phi integral, you've got a rho squared over 4 times 2 pi, which is rho squared over 2 times rho squared pi over 2 and all that stuff. So I'm not going to go through the details of the integral because I'd probably get careless and write something ignorant down if I haven't already. But it seems like you have a pretty straightforward integral here.